Hi, this is our presentation for the project. So the motivation for our project comes from the observation that in the field of image classification, two main architectures have dominated, which are transformer architectures and convolution architectures. Now, transformer architectures excel at their high accuracy and robustness, while convolution architectures make a better trade-off in terms of efficiency and the parameter size. So our motivation is this: what if we can combine the advantages of both architectures into one model? Next. And guided by the motivation, we propose three baselines. First, we have Swing V2, a pure transformer architecture that uses hierarchical feature maps. And they also propose several small improvements listed on the slides. Next. The next baseline is Convex V2, a pure convolution architecture that has a global response normalization layer, which is the improvement they made on the original convex architecture we've seen in our homework. Next. The most important baseline is the convolutional transformer, which combines both transformers and convolutions by having a convolutional token embedding and a convolutional projection layer in a transformer block. We propose that with our improvements, the CvT will achieve high accuracy and also maintain low parameter size. Next. So the dataset we use is ImageNet 100, which is a subset of ImageNet 1K. Here are the number of samples of train belt and test listed on the slides. Next. So
So,
now we present our improvements.
so the first improvement we add is rotary positional embedding, and RoPE integrates relative positional embedding through rotation matrix product to capture the relative positioning between tokens instead of injecting this positional information through addition. For input X with D dimension, we split it into D divided by two parts, so we can express X as a complex number. For each token at position K, we apply a rotation matrix characterized by the angle theta k. The embedding for position k is rotated by multiplication with the complex exponential. The key benefit of RoPE is that it has relative positional invariance, and then we can pre-compute a set of angle theta for each dimension I. And we've tested this RoPE added CvT and compare it with the baseline CvT, and the metrics that we use to compare is the top one accuracy on the validation set. So we show that the RCVT has a greater validation top one of 86.82 compared to the baseline CvT, and we haven't even run as much epochs as the baseline CvT.
The second improvement is deformable attention. Next. So compared to normal attention, deformable attention has a larger receptive field and use less computation. Instead of using the full feature map, deformable attention use a bunch of reference points to sample the feature map and downscale the feature map. What makes it unique is that there is an offset network used to predict the offset of each reference point. In this way, the sampled feature map can uniquely adapt to different shapes. And after that, the feature map will be transformed into value and key matrix and perform the standard attention. Next. So in this way, our validation accuracy is 86.81, which beats the baseline by 3%. Next.
Let's dive into the results next. Starting with the baseline performance of CvT models, we validated the accuracy claims across different resolutions and found our replicated results closely match the reported numbers. This gives us confidence in using CvT as a solid starting point. We then compare CvT with newer architectures like ConvNext and Swing Transformer. While these models demonstrated competitive performance, CvT still held its ground, especially given its balance of accuracy and efficiency. ConvNext, in particular, showed gains at higher scales, but the computational costs were also higher. Next. To push CvT further, we introduced optimization like deformable convolution and rotary position embedding, resulting in deformable CvT and RoPE CvT. This change has significantly boosted accuracy while maintaining efficiency. This highlights how target innovations can enhance performance without a major increase in resource usage. In conclusion, our optimized CvT models not only close the gap with newer architectures, but also offer a compelling trade-off between accuracy and computational cost. This demonstrates the potential of CvT to remain competitive in modern computer vision tasks.
Thank you. That's the end of our presentation.